So hello everybody, I am Io Di Antonio, mechanical engineer, PhD student of University of Rome, and I work in INAF, Osservatorio Astronomico d'Abruzzo, with my colleague Gianluca Di Rico and Mauro Dolci. We are responsible for the design of MAORY Calibration and Test Unit. So a few words about MAORY, the multi-conjugate adaptive optic system for the ELT telescope. Here we can see the MAORY bench and the optical design of MAORY. Actually, it is not the very last version of the design, since there is also, again, still open discussion about the optical design. Anyway, we can appreciate the position, current position of the CTU, calibration and test unit, which is now positioned next to the telescope focal plane in this space that is free. Yeah, we hope it will be free. And some information about MAORY. We have here the optical relay, two deformable mirrors, the LGS wavefront sensor module, and the NGS wavefront sensor module. So calibrations are very important to remove the instrumental signature from the scientific data, and it's important to be managed the calibration at the system level, so collecting the inputs from all subsystems, flowing down calibration technical specifications, and defining a calibration plan. Calibration in MAORY consists in functionalities check and out-loop parameters calibrations. So about functionalities checks, we have the wavefront sensor characterization, so checking parameters like linearity, dynamic range, faint and bright regimes, flatness, gain, and readout noise. We have also the pupil check, so misregistration, rotation, illumination uniformity, and sampling, and also optical system check, like for example, the overall transmission of the optical system. We have to calibrate also the out-loop parameters, so non-common-path aberrations, calibration, static, quasi-static, and dynamic, and the interaction matrix construction. So briefly, focus on MAORY wavefront sensors calibrations. We have, of course, for both the LGS and the NGS wavefront sensor, a periodic health check. Then we have for the LGS reference slopes calibration, the slope response of each subaperture, the measurement of unvignetted field of view, interaction matrix, pupil positions, and verification and test of wavefront sensing algorithms. Also for the NGS wavefront sensor, we have field mapping of lower acquisition stages, the interaction matrix of each active elements of the lower wavefront sensor, and also, again, the verification and test of wavefront sensing algorithms. Okay, we have two different subsystems in MAORY dealing with calibration, testing, and verification. The CTU, our subsystem, calibration and test unit, it will be installed in the telescope and is developed by INAF. And of course, it has tight constraints in terms of mass and volume, fluxes, and so on. The main task has already been described in the previous slides. We talk of functionalities check, post-focal, DMS interaction matrix construction, non-common-path aberration, and it's important that this subsystem for this subsystem at the moment is not asked to provide alignment, source for the alignment of MAORY. We have also another subsystem, the test and verification unit, which is an IV tool and developed by the University of Galway. The main tasks of this system are AO performances verification, software functionalities checks, and so on. So just to say this slide that these two as different subsystems, but they walk in parallel. We are also thinking to share at least a part of the optical design. So the main task of the calibration and test unit is providing proper light sources with well-known features for AO calibrations. And at the moment, the CTU is asked to provide a grid of several NGS sources with the following features. Uniformly distributed within the NGS wavefront sensor technical field of view, which is 60 arc seconds. sufficiently bright to cover a wide range of magnitudes from 5 to 22, and diffraction limited in H band. It also has to require a set of LGS extended source, 3 arcseconds, distributed on 4 asteroids with pupil rotation. Each asteroid is conjugated with 4 specific altitudes on sky, 8 sources for each asteroid, and the wavelength of sodium. It also has the possibility to use at the same time both NGS and LGS sources, obviously meeting the optomechanical constraints. So in this table, I've briefly summarized the features of the sources, in particular the diffraction limited for the different bands of the NGS wavefront sensors. We have calculated, esteemed the stray ratio of at least 85% for these natural guide star sources. And we have also calculated the flux range in photons per second equivalent to this range of magnitudes. Yeah, more or less the same for the LGS sources. Okay, so here I want to show the architecture of the calibration and test unit. So we have the physical light sources, white broadband sources, and laser sources. And these physical sources are positioned into the electronics cabinet, together with a set of flux and fiber selectors, whose function is to adjust the flux of the sources and to eventually select the output fiber. A set of fibers is stretched from the electronics cabinet, which is positioned 6 meters, about 6 meters below the MAORY bench, up to the MAORY bench, where 2 different masks, mechanical masks, with all the sources are positioned. We have 2 different masks, one for the NGS sources and the other one for the LGS sources. And the final number of sources is obtained by splitting these fibers. For the NGS sources, we are also considering the possibility to obtain the final number of sources with this solution, so diffuser and the final masks, but it depends on the required flux, which is not yet confirmed. Okay, so just to summarize the parts of the calibration and test unit, source mask unit composed by 2 separated masks, one for the NGS and one for the LGS. In such a configuration, we have shorter axial sides, and most important, we can image all the sources together without vignetting. Of course, this solution needs a beam combiner. Then we have a focusing optical system to adjust the optical features of the light to fulfill the optical requirements, and we will see in the next slides. And finally, a folding mirror positioned before the telescope focal plane to inject the flux into the telescope light path. So I will focus more on this optical system because in this stage of development we have considered the mechanical design subordinate to the optical design. So a set of optical constraints: the light from the CTU has to match the ELTF numbers, ELT focal plane curvature radii. The NGS light sources has to be diffraction limited on the telescope focal plane. The LGS sources have to be extended on the laser focal planes, and pupil have to be created in a nominal proper position. We have considered also a mechanical constraint on the axial size of the system, which is 2 meters to be confirmed. The concept of this system is to use 2 lenses. First lens, which is an objective at pupil stop and provides the proper F numbers, and the second lens, which is positioned close to the telescope focal plane. It's a field lens and provides the proper pupil position. In the Zmax, the merit function operands defined are the radial position of the sources on the focal planes, the F numbers, and the pupil positions. So these are the targets that we want to achieve. And the optimization outputs, so our variables, are the axial position of the lens 1, of the sources masks, and the radial position of the sources on the masks. So here we can see a first guess with no constraints on sides. We have here this second design is just a zoom of this first part. So we have the physical mask with the sources here, the NGS mask, and the LGS mask, which is just one mask movable to cover these 4 altitudes on sky. We have this first lens, still paraxial, working also as a pupil stop, and a second mask, a field mask, very close to the telescope focal plane. Later, we will have to add a beam combiner here and a folding mirror here. So in this first guess, more or less meets the requirements in terms of the quality of NGS, diffraction limited on axis, the F numbers, pupil position, curvature radius, sources position. So basically all the requirements except the axial length, because it is 4 meters, so definitely too long. So we have tried to force the axial sides into the merit function, but the result is not okay because we lose the precision of the F numbers and sources position on the focal plane. So in the next guess, that will be coming soon, we are going to move the NGS sources in this location, so at 90 degrees to the optical axis, to recover this length. And we are also going to move this first lens 1 here in this path, so separating the NGS and the LGS path. I mean, just this can be done. I mean, the optimization of the lens 1 in this case is just for the NGS case. And the lens 2 remains very close to the telescope focal plane, so it has a very limited impact on the NGS. In this case, we will reduce the axial length. So we have also defined a CAD design of the electronics cabinet to understand the necessary volume, and we have selected the type of cabinet. We have also defined a possible layout of the racks inside. I remember that we have put inside the cabinet the physical light sources and the selectors. The selectors in particular are shown here, and then are simple mechanical components with a filter which can move through a linear stage, and the output that can eventually move through another linear stage. So last slide, just to define the road to PDR for the MAORY calibration and test unit. The architecture of the CTU has been defined. The optical, mechanical, and electronics design, a draft of them have been started. We have found the components of the shelf and started contacts with the companies. Next steps to do are the optimization of the optomechanical model, an optimization based on the flexibility, on approach on flexibility. First defining the paraxial configuration of the system, then turning the lenses from paraxial to real, so then folding the optical design to a reasonable volume, build the mechanics around this optical design, and finally checking if this design is compatible with the MAORY optical design. It's also important to starting as soon as possible prototyping and test activities for the whole transmission chain, so physical sources, fiber splitters, and fibers, and designing test apparatus for the future AV phase. So that's all. Special thanks to Lorenzo Busoni for his support on the optical design, and thank you all for listening.